Good morning, everyone. I'm Andreas. I'm very happy to be here with you in Dublin. It's my first time here in Dublin, so I'm double excited. I know it's early, and it's the last day of the conference, so at this point, probably your brains are running a bit lower and on caffeine. So I promise not to run any heavy workloads on your brains before coffee kicks in. Originally Greek, the last 15 years I'm based in Amsterdam, Netherlands, with slightly less than 20 years of experience in different types of companies. The last almost 4 years I work with GitHub in the performance engineering team, where we try to make GitHub faster and more efficient while scaling it to 10 times its current scale. Before starting, can I get a feeling of how many do you think GitHub is fast? Can you raise your hand? GitHub is fast. Is it fast? GitHub is slow. Yeah? I think I saw more hands with fast, so maybe we're doing a good job. I don't know. We'll see. Without further ado, let's jump to our agenda for today. We'll start with some fundamentals of performance theory, setting the stage for why CPU and latency matter so much in modern systems. Next, I'll share how performance is approached at GitHub, what we focus on, and how we observe growth. We'll then look at practical techniques for measuring CPU usage, both at the system and the application level. And after that, we'll connect CPU utilization to latency, exploring how changes in CPU load can impact response times and overall user experience. Finally, we'll discuss how to find this sweet spot for CPU utilization, where you maximize efficiency without sacrificing performance. Hopefully, after this talk, you will have a better understanding of how different concepts like capacity, latency, and CPU utilization are connected and affect each other. Let's start with what is performance. When we talk about performance, it's important to remember that it's not just a number or a metric. It's a concept with more than one dimensions. Meaning that there are several key aspects we need to consider in evaluating how well our systems operate. First, there is latency. This is about responsiveness. It's the time it takes to serve an individual request or complete a specific operation. Users notice latencies directly, especially in interactive applications. Next is capacity. This represents the maximum workload or throughput of our system that can sustainably handle, and it's our ability to process requests at scale without failing over or causing any delays. And finally, we have efficiency. This is about how economically we deliver the throughput and latency. It means using resources, energy, and budget wisely. And a system that is fast but burns unnecessary resources, it's not really truly high efficient. So as we assess performance, we need to look at all three dimensions together, focusing on only one, like, for example, latency, without considering capacity or efficiency can lead to costly mistakes or missed opportunities. We've seen how performance isn't one-dimensional. It's shaped by latency, capacity, and efficiency. But these dimensions don't operate always in isolation. They are tightly interwoven by the underlying queuing dynamics in our system. And to understand this connection, we can turn to one of the core theorems in queuing theory, which is the Little's Law. We are highlighting Little's Law here because at GitHub we use it extensively to monitoring our utilization and assess our system's capacity. It's a core tool for understanding and optimizing the interplay between incoming demand and our ability to serve it efficiently. Little's Law tells us that the average number of active requests in our system is equal to the arrival rate times the average latency. As we tune our systems, we need to consider how changes in one dimension, like for example latency, ripple through the others, affecting overall performance. Now, since we are currently in an AI hype, I had to use Copilot to create an image for you all. This is an AI-generated image that can show us Little's Law through an everyday example. So imagine a coffee shop where on average 40 happy unicorns customers arrive per hour. Each unicorn spends 6 minutes in the shop. And using Little's Law, we can see that at any given time, there are 4 unicorns in the shop. This helps the owner understand how many people are typically in his shop and plan staffing or seating accordingly. Think about something like capacity planning for coffee shops. Applying this law now in our field, we can also observe the utilization of a system. This is one example of one of GitHub's workloads where we can use a couple of metrics to identify a system's utilization. Using our arrival rate and the latency of each request, we can see how many requests we have inside our system at any given time. These metrics may come potentially from the same metric, but applying different aggregations depending on your monitoring tool. The first two metrics, A and B, shows us the arrival rate and the latency. Now that we have determined how many requests are active in our system at any given time, we can compare this number to the total amount of available processes or workers that we have. The metric C shows us the available workers, and below we use Little's law formula to calculate utilization. In a blocking-based system, each worker can handle only one request at a time. So if the number of concurrent requests exceeds the number of workers, requests start to queue, leading to increased wait times and higher user-facing latencies. Now that we've given a definition of what is more or less performance, and we have seen how we can look at our utilization through Little's law, let's look at how these ideas can be seen in a larger scale real-world system like GitHub. As GitHub has scaled over the years, we've naturally seen an increase in system latency, like more users, more repositories, and more requests all put pressure on our infrastructure. Recognizing this, we have driven many performance-focused initiatives over the years, from targeted optimizations to broad architectural changes. About 2.5 years ago, we formalized these efforts by establishing an official performance team. This team's core mission is to build and maintain efficient systems that can keep pace with GitHub's rapid growth. Our main priorities are to reduce and sustain low latency, maximize CPU efficiency, and ensure our systems have the capacity to meet the demand. Achieving these goals requires close collaboration across all the teams in GitHub, basically. Performance isn't something that we can tackle alone. It's a shared responsibility for everybody in the company. By focusing on efficiency and capacity planning, we can deliver a smooth experience for our users even as GitHub continues to expand. Now, let me give you some context on how we started looking at our CPU performance and what led to our experiments. This graph illustrates the consistent growth in GitHub's traffic over time. While we occasionally see spikes, the overall trend is a steady increase. And as our user base and activity grow, we are consistently handling more requests, reflecting GitHub's expanding role in the developer ecosystem. This ongoing growth that we see here is the key driver behind our need for continuous performance improvements and capacity planning. We always need to remember that scaling efficiently isn't a one-time challenge, but it's an ongoing process that as demand keeps rising, that we should always have in mind. Alongside the growth in overall traffic, we are also seeing a steady increase in application utilization. This means our core services are running hotter, handling more work as demand continues to rise. Rising utilization puts pressure on our systems to remain efficient and performant, and it's another reason we must continually monitor, optimize, and plan for capacity. Now, as this graph shows, latency is also not very consistent. It can trend upwards, especially during peak demand or when system resources are stretched. Tracking latency helps us also to identify emerging bottlenecks or inefficiencies before they impact our user experience. Admittedly, not always before, but this is our wishful thinking. And our goal is to quickly spot and address these increases, keeping latency as low and stable as possible, even as GitHub grows. In addition to rising traffic, application utilization, and latency, we're also seeing steady growth in overall CPU usage across our systems. This reflects not just how many more requests we serve, but also increased computational demands from new features and larger workloads. As CPU usage climbs, it's critical to keep optimizing our application and infrastructure to maintain efficiency and prevent any kind of bottlenecks. Monitoring CPU trends helps us plan for scaling and ensures we are making the most of our hardware resources as we expand. In these two graphs, we are zooming in on a couple of weeks' worth of data, and we are looking at CPU utilization and latency side by side. You can see that when CPU usage increases, then latency tends to follow. These metrics move together and they are tightly linked. This relation highlights how system load affects response time, and as our CPUs get busier, requests take longer also to process. Understanding this connection guides our scaling or optimization decisions, and it's a reminder that managing CPU utilization is key to keeping latency under control and a core part of maintaining our performance. It was actually this correlation that sparkled as our experiment, prompting us to examine the impact of CPU utilization on our latency. Now that we have explored some of the performance theory and saw how latency and CPU are related in GitHub system, let's shift our focus to how we actually measure things. How do we actually assess and capture the CPU performance in such an environment? You may ask, of course, why it's important to measure things at this level and complexity. The answer is that we wanted to dig deeper and pinpoint exactly how far we can push our systems to maximize efficiency without overspending or under-provisioning our infrastructure. So we saw that we recognized a clear correlation between high CPU utilization and increased latency, something both our data and our intuition suggested. Having more than one instance type and CPU families in our infrastructure, we wanted to examine and understand the unique performance characteristic of each model. And this deeper investigation allowed us to identify optimal thresholds for performance, ensuring that the best possible user experience. Using these insights, we were able to make smarter and data-driven decisions and provision our infrastructure with greater confidence and efficiency. Now, collecting accurate data for this experiment was a challenge. To ensure our findings were meaningful, we had to use workloads that closely mirrored production, including our monolith. Capturing system behavior under different load phases was another requirement, since CPU usage varies widely across workloads and CPU families. But most importantly, we were committed to avoid any impact on our experience, in our user experience. Maintaining reliability was not something that we took for granted. It was a top priority for us. Fortunately, about 2 years ago, the performance engineering team developed an environment designed to address most of our challenges, a dedicated performance environment. This environment replicates our production setup in a controlled, isolated slice of our clusters and can even run on dedicated hardware when needed. Most of the time, the environment is idle, but we can instantly route traffic to it, observe performance, and then shut it down just as quickly. This flexibility allows us to experiment and respond to performance concerns without impacting our users. Now, this high-level diagram illustrates how incoming traffic is routed to our performance environment. User requests first hit the GLB load balancer, our global load balancer, which then distributes them across our Kubernetes clusters. Crucially, we have the ability to write a very small controlled fraction of this traffic to our dedicated performance environment. It can be as 0.1% till a percentage that we can actually saturate this workload. This setup allows us to run experiments and gather performance data on production workloads without impacting these workloads. And it gives us a flexibility to test, validate, and also tune performance in isolation, ensuring both reliability for the vast majority of our users and valuable insights for engineering. Now, moving on to another important part, how do we actually measure our CPU? This is important because it allows us to get more complete data and data that actually trust and can drive decisions. To understand CPU performance and efficiency, we focus on two key metrics. First, the system CPU time, and then the application CPU time. Now, let's start with how we measure the system-level CPU metrics. For each of our nodes, we collect metrics directly from the operating system. These are the same sources used by most infrastructure monitoring tools. It's not something custom to us. We read from files like /proc/stat, which gives us a breakdown of CPU time spent idle, busy, or in different states. And this is how we track total CPU utilization and idle time across the whole node. For more granular data, we can look at per core metrics, including how busy each specific core is and what is the current operating frequency is. For frequency, we use the second path, the sys devices system scaling current frequency. But you have to remember that not in all, for example, in cloud VMs or certain CPUs, you will not be able to find these files. So it might be kind of tricky to get it. This metrics gives us a high-level view of node performance and resource usage, but they don't tell us what's happening inside individual applications. In order to see what is happening inside individual applications, we use another approach. And this slide shows how we measure CPU time from this side, which gives us a much finer-grained understanding of CPU usage. We use clock getTime, clock process CPU time ID, which acts basically as a CPU time counter for each process. Every time a process uses CPU, this counter increases, reflecting only the actual time spent in CPU, not time waiting on I/O or being idle. And to measure the total time for each request, we record the counter value at the start and at the end of this request. Subtracting now the ending value from the starting value gives us more precise CPU time used to handle this request. In the diagram, you can see the two parallel lines, which are the unicorn processes. And each of these processes, a unicorn worker, handles only one request at a time, and their CPU counters are tracked independently. For example, request B starts at counter C3 and finishes at counter C3. So the time it spends on CPU is C3 minus C1. By measuring CPU time this way, we can separate out time spent waiting for external resources and focus only on the time our application is actually using CPU cycles. Lastly, let's see what were our measurement process, right? What steps did we follow to make our experiments matter? As in many measurements, we wanted to get a baseline for our comparison. So we began by routing moderate production traffic to a specific node, and that would be the baseline that we could compare as CPU utilization was growing. Maintaining a steady request rate was crucial, and it helped us isolate the effect of CPU load. Next, we gradually increased CPU utilization using a stress tool called StressNG, if you know, which basically simulates CPU-intensive tasks and drives CPU utilization high. And since each instance type has a different number of CPU cores, we adjusted our approach accordingly, but kept the CPU utilization as the common factor across all our tests. And this methodology gives us clean comparative data to analyze the relationship between CPU usage and performance. So now that we've covered our experimental setup, discussed how we measure CPU usage both at the system and application level, it's time to look at what those measurements reveal. The main question we set to answer was how and why does CPU utilization impact latency in our application? In this next section, I will present the results of our experiment, where we will see how increasing CPU load affects response time and what factors contribute to our CPU performance that leads to latency increases. Let's start by looking at some of our findings. This graph shows the median, the P50 time, that each request spends on CPU as CPU utilization increases, comparing 3 different CPU generations. You'll notice that each CPU gives us different baselines. So Gen 5 starts lower, and then it's Gen 4, and then it's Gen 3, which translates directly to higher latency for application requests. What's interesting here is that each generation responds differently. For example, the Gen 5 CPUs maintain lower latencies up to a higher utilization, while Gen 4 or Gen 3 see sharper increases as they approach saturation. You'll notice that each CPU generation displays also its own characteristic patterns, with a distinct point where the rate of latency increase becomes much steeper. And this highlights that every CPU reacts slightly different as utilization increases. This data now confirms our hypothesis that pushing CPU utilization too high leads to significant latency penalties, and the threshold varies by CPU type. So as we provision infrastructure, it's important to account for these differences to avoid unexpected performance degradations. Similar to the previous slide, here we see how much more CPU time we use compared to its lowest typical point, so the baseline. So the lines now, the y-axis, instead of having their own numbers of latency, they give us the percentage increase. This view helps us see not only the actual latency numbers, but also how things get slower as we use our CPUs more. Both the Gen 5 and Gen 4 CPUs shows a steep climb in latency once utilization passes about 40%. And at high utilization, requests on these CPUs can take 50 to 60% longer compared to the baseline. Gen 3, represented by the blue line, behaves slightly different if you see. It remains relatively flat until the very highest utilization levels where it starts to climb as well. And this is a clear outlier where I'll discuss more about this in the next slides. But overall, this chart makes it clear that for most CPU types, running them close to saturation has a major impact on latency. And the performance increases is a useful way to quantify just how much performance degrades. Now that we've seen how latency increases with CPU utilization, let's explore what is happening under the hood that can cause this type of behavior. This chart shows how the frequency of individual CPU cores changes as overall CPU utilization rises. Modern CPUs use dynamic frequency scaling. For Intel technology that we have, this is called turbo boost. I think maybe other CPUs also have something different, something similar. And they use dynamic frequency scaling to temporarily increase their speeds when demand is low and thermal or power limits allow. At lower utilization, you can see that the cores run at higher frequencies, and this is a turbo boost effect, which allows tasks to finish quicker, and the time spent on CPU is much smaller. That keeps overall latency low and performance high for bursts of activity. However, as many more cores are engaged and overall CPU utilization increases, the processor approaches thermal and power limits, and to stay within these constraints, it automatically reduces its frequency. And this frequency drop means that each task now takes a bit longer to complete, and we see latency increase as utilization climbs. Essentially, lower CPU utilization gives us better performance, while higher utilization causes performance to degrade. For example, the same workload running at 30% CPU utilization will consistently deliver faster response times than when it's on a node that is pushed above 50% utilization. Now, after examining the turbo boost effect and its impact on CPU frequency and overall application latency, our next observation focuses on what happens when CPU utilization gets even higher. And looking at the frequency graph, we see that after about 60% CPU utilization, the CPU frequency plateaus, so it stops dropping, even as we push utilization up to 80% and beyond. However, if we look at our application CPU time and latency, they continue to climb sharply past this point. This discrepancy points us to another underlying factor, which in Intel technology is called hyperthreading. This effect is clear in the latency graph. So after the frequency flattens, latency keeps increasing, showing the limits of what hyperthreading can offer for high throughput workloads. Recognizing this behavior helps us understand why latency doesn't just track frequency and why there is a noticeable increase in latency once the turbo boost effect is no longer active. Let's talk about a bit more about hyperthreading and how it affects our latency and our CPU performance. As before, this is only a technology in Intel. I think other CPUs will have probably similar, I guess. Hyperthreading is an Intel technology, as I said, that allows a single physical CPU core to appear as two virtual cores or hardware threads to the operating system. And this enables more tasks to be scheduled simultaneously, increasing throughput in certain scenarios. The kernel works to balance the load across these virtual cores, ideally keeping only one hardware thread busy per physical core. This helps prevent resource contention and keeps performance high. However, this approach is effective only up to a point. when CPU utilization rises and our load average exceeds the number of our physical cores, both hardware threads per core become active. And at this stage, the two threads begin competing for the same physical resources, which can lead to reduced efficiency and increased latency. This explains the continued growth in application CPU time and latency we saw on the previous slides, even when CPU frequency remained flat. Hyperthreading helps us squeeze more work out of each core, but it also introduces contention that can degrade performance at high utilizations. Understanding this transition point is crucial for capacity planning and performance tuning, as it marks the boundary where increasing load starts to behave a disproportional impact on latency and efficiency. A good rule may be that every time you see a machine having a load average that is higher than the number of physical cores, you can potentially observe and assume that there is going to be a slowdown caused by CPU oversubscription. Now, let's revisit the previous graph where we saw that one of our CPUs didn't behave as the other ones. We noticed that something was unexpected, right? For one of the CPUs, the blue one, latency remained almost flat, even as CPU utilization increased. And this contrasts sharply with other CPUs where the latency rose steeply. This anomaly caught our attention, and we wonder why doesn't this CPU behave like the rest? The increase was more pronounced after 65%, which is approximately where the impact of hyperthreading begins. However, we didn't observe any noticeable turbo boost effect. Digging deeper, we discovered that the answer lies in the CPU's power management, specifically in the C states. When examining the CPU frequency of on this instance, we observed something interesting. According to the CPU specs, we should expect turbo boost frequencies above 3 GHz. However, as you see in the graph, the maximum frequency we observe never goes beyond 2.8 GHz. The issue turned out to be caused by a disabled CPU state. I don't know if you know what is CPU states, but I'll go through that for a bit. CPU states are idle power modes for processors, allowing the CPU to progressively power down parts of itself to save energy when workloads are light. Turbo boost, on the other hand, is designed to temporarily raise the clock speeds above the base frequency when and only when there is enough power and thermal headroom. With C states now disabled, idle CPU cores were unable to enter deep, low power modes, and as a result, the CPU's overall power consumption remained high, even when workload was low. This higher baseline power usage limited the available power and thermal headroom for turbo boost to activate. By enabling C state, we allowed it for optimization and power reduction during idle periods and enabled the turbo boost behavior as expected. These images here show how CPU frequencies responded promptly after the C state adjustment. After retaking the same experiments and plotting our CPU time versus the CPU usage graphs, we observe consistent behavior across all CPUs. Now we see that the blue line is kind of moving like the other two. And with this adjustment, both the turbo boost effect and the hyperthreading was clearly visible in our data. Now that we've seen how and why CPU utilization impacts latency and overall performance, the next question is how do we actually balance efficiency and responsiveness in a large-scale environment? As our result shows, both underutilized and overutilized utilization of CPU resources come with significant drawbacks. Underutilized nodes waste power, space, and money in our data centers, while highly utilized nodes can suffer degraded performance, potentially misleading us into scaling up unnecessarily. This cycle is especially problematic for blocking workloads, which are less efficient than asynchronous ones sometimes. When CPU performance drops, each process handles fewer tasks per second, making our existing capacity seem insufficient. And to break this cycle and maximize our efficiency, we aim for a golden ratio, a threshold of CPU utilization that is high enough to avoid waste, but it's not so high that performance suffers. And by operating close to this sweet spot, we can make the most of our infrastructure and avoid costly over-provisioning. Having all the data is one thing, but now the real question becomes, how do we actually define the optimal utilization threshold, the sweet spot for our systems? The answer, unfortunately, to these questions cannot be the same for each system. It varies and it can potentially be different for each environment. But in order to find it for a specific system, we should start by measuring both application level and system level CPU time across a range of utilization levels. This gives us a full picture of how our workloads behave and perform as we increase the load. Next, we need to decide what level of CPU degradation is acceptable for us. This is typically based on our SLAs or our user experience expectations. For example, we might allow a 10% or a 20 or 30% increase in latency before performance is considered unacceptable. We then plot CPU utilization against CPU time and look for the knee point, the threshold where performance starts to degrade more rapidly than our acceptable limit. And the goal is to find the utilization level that maximizes efficiency, using resources as fully as possible without crossing the line where our user experience or SLAs are compromised. And by following this process, we can set practical, data-driven utilization thresholds that balance cost, efficiency, and performance for each CPU type and workload. Now let's walk through a concrete example of how we define the utilization sweet spot for a specific CPU type, right? On this graph, the blue line shows the percentage increase in median application CPU time as we ramp up node CPU utilization. We've set our acceptable degradation threshold at 40% based on our SLAs and what we know about our user experience. And this is represented here by the red dotted line. Our goal is to find the highest CPU utilization we can sustain while keeping CPU time degradation below this threshold. As you can see, the green line marks the point where the blue curve crosses the 40% threshold. And for this instance, that happens to be at around 61% CPU utilization. This golden point is our optimal utilization threshold. It allows us to maximize efficiency and minimize cost while ensuring performance stays within acceptable limits. By repeating this process for each CPU type and workload, we can confidently set utilization targets tailored to real-world behavior and requirements. And we made it to the end. To wrap up, I want to leave you with a few practical points to remember from today's talk. First, always pay close attention to performance. Make data-driven decisions and don't rely solely on intuition or default configuration. Measure CPU usage from both the application and system perspectives if you can. It's important to understand not just how busy your CPU is in general, but also how your application is specifically consuming the CPU resources. Dig into your CPU's actual performance characteristics. Don't just trust the datasheet specs. Real-world measurements can reveal surprises and outliers, as we saw. Watch carefully for the knee in the CPU utilization curve, that inflection point where latency starts to rise sharply. This is your signal that you are leaving the safe zone and entering an area of potential performance degradation. Review your metrics regularly and look for trends and patterns. Early detection means you can act before users notice any problem. Now, if you take nothing else away, let it be that these 3 points. Understand how latency correlates with CPU utilization. Learn how to accurately measure application CPU usage and know how to identify and operate at the CPU utilization sweet spot for your environment. Thank you for your attention. I hope these insights help you build faster, more reliable systems. And that was it. Thanks a lot for being here. I hope you got something useful. For those of you who love stickers, I have a bunch of cool GitHub stickers with me. I'll be happy to give them out before I leave. So feel free to find me after the session or during the break. And I'll be happy to give it out. This talk was based on a public blog post we published last year in GitHub's blog. If you want to read that, feel free to visit that page. And now I'm happy to take any questions.